Greetings. So, welcome to today's class. So, let us continue from where we left off in the previous class. Let me start with a brief recap. So, if we recall, we were looking at various types of systems and also various types of inputs in the previous class, and then like we looked at what is a linear time invariant system and what are the different standard inputs that one could consider to analyze systems and so on, right? So that was the those were some concepts that we discussed, and then we looked at a simple example of a mass spring damper system and wrote down the equation of motion for that system, which serves as its mathematical model. And we just identified when it could become linear time varying, non-linear, and so on, right? So, and then we stop with the question, so how do we solve these ODEs to analyze the system? Okay. So, typically what we can do is that like we can solve ODEs in the time by staying in the time domain itself. We can also use the theory of Laplace transform, right? So to essentially solve ODEs. So in today's class, let me briefly discuss, the theory of Laplace transform and its application to our analysis, right? So before we go to Laplace transform, let's quickly recap what a complex variable is. So if in general, a complex variable can be uh, denoted by its real component and the imaginary component, right? So let's say we have a complex variable S, right? We could write the complex variable S, sorry, S as some sigma plus j omega, where j squared is equal to -1. Okay, so that's how it is. So sigma being the real component, j omega being the imaginary component, right? And when we plot this complex variable, yes, that two-dimensional plane is what is called as a S plane. Okay, so these are some terms that we should remember. A real variable can go from -infinity to +infinity, right? But a complex variable can be represented in the two-dimensional plane as shown here, right? So, for example, if we look at time, time is a real variable, right? So, essentially, we can, in theory, it can go from -infinity to +infinity, right? And we can represent it on a 1D axis, one-dimensional axis, right? So, on the other hand, a complex variable, we need two axes and we can represent it in a plane. So that is a fundamental difference. So when we talk about the Laplace transform, the Laplace transform essentially transforms a function defined over the field of real numbers to a corresponding function defined over the field of complex numbers. So the question arises why we would do such a thing, right? So let's quickly run through the definition and some few properties of Laplace transform before we figure out how it is useful and how we are going to use it, right? So in our analysis. And also, as we go along in this course, how it is useful in vehicle dynamics, right? So that's something which we'll figure. So the Laplace transform function f of t is defined as a follows. L of f of t, script L indicates Laplace transform, f being some function of time. Okay. T, of course, can be any real variable. In our course, we are looking at time as the independent variable. So I'm just considering T as time, right? Laplace of T, let's represent it by capital F of S. So the notation that you follow is that like in the time domain, I will write the function using a lowercase character. In the complex domain, we will use the corresponding uppercase character. Okay, so that's what we will do. And this is going to be, this can be written as minus infinity to plus infinity f of t e power minus st dt. Okay, so this is what is called, this is the definition of the Laplace transform. This is what is called as the bilateral Laplace transform. Okay, so the reason it's called as the bilateral Laplace transform is that you can see that the limits of integration, right, go from minus infinity to plus infinity. So that is why it's called bilateral Laplace transform. Okay. Uh, but of course, in our course, since we are going to consider t as the independent variable, right? So when we start a process or when we look at a phenomena, we are going to consider the initial time as t equals 0. So we will use this definition of Laplace transform. So which is given by this Laplace of f of t is going to be 0 to infinity f of t e power minus st. Okay, so this is what is called as the uh, unilateral Laplace transform. Okay, so the reason why it's called unilateral is because we can immediately observe that this is the limit of the integration is from 0 to infinity. Okay, so that is why it's called unilateral Laplace transform. Okay, so we will be using this definition. And I'm going to leave something as an optional exercise to you. So I'm sure this is something which you can easily do. So I'm just going to write a table of Laplace transforms, which is pretty standard, and I'm sure that you can use the definition of the Laplace transform and then get these expressions and check for yourself. Okay, so that's something which you can certainly do as an exercise, an optional exercise. Okay, so that you can learn from it. Okay, so what are some standard forms that we are going to consider? So let's say we take the unit impulse function or the Dirac delta function delta t. If we apply the Laplace transform to it, we get 1. Okay, and if you get the unit step input or 1, we will get 1 by s as the corresponding Laplace transform. If we take the unit ramp signal t, okay, we will get 1 by s square as the corresponding Laplace transform. Okay, if we take e power minus at, then we are going to get the Laplace transform as 1 by s plus a. Okay, if we take the function as sine omega t, okay, so we are going to get the Laplace transform as omega divided by s square plus omega square. Okay, and if we take the function in the time domain as cosine of omega t, this Laplace transform is going to come out as s divided s square plus omega square. Okay, so these are a few commonly used Laplace transforms. Okay, so once again, these expressions could be obtained by using the definition of the Laplace transform, right? So just substitute it in the definition that we wrote down at the top, and then we will be able to get these expressions. Okay, so pretty straightforward to do. Please do try them out. If you have any questions regarding these properties, please do let me know. Okay, and then we can certainly discuss. So I'm just going to quickly write down some properties of Laplace transform that are going to be useful for us in this particular course. So let me quickly write down. The first property is that of Laplace transform of derivatives. So if the Laplace transform f of t is f capital F of s, if we consider df dt, right, the Laplace transform is going to be equal to s times capital F of s minus small f0. Okay, where f of 0 is nothing but f of t evaluated at time t equals 0. Okay, so that's what it is. All right, so we are essentially dealing with the transform of the first derivative, okay, of a function. Similarly, if we have a second derivative, right, b squared f of t dt square, right? So if we have that, this Laplace transform is going to be s squared f of s minus s f times 0 minus f dot 0. I just shortly write down what is meant by f dot 0. So where f dot 0 is nothing but df dt, evaluated at time t equals. Okay, so that's what it is. All Right? So that is the Laplace transform of the second. So this we'll by and large use the Laplace transform of the first derivative and the second derivative. So that's why I wrote written down only these equations. Of course, one could go on, right? Third, fourth, fifth, and so on, right? In general, we could write the Laplace transform the nth derivative. Okay. So then a few more properties, like the second property which I'm going to write down is what is called as the final value theorem. So what is this final value theorem? The final value theorem can be used to figure out what will be the value of a function of time as time tends to infinity. Okay, so this is pretty useful, right? Because see, if one wants to evaluate, let's say we are doing some experiment using a vehicle, right? Let's say we are doing some cornering experiment, right? We give a steering input. We want to find out, if I wait long enough, right? So what will be the change in the heading angle of the vehicle, right? So then we can use the final value theorem. So essentially what happens is that like limit t tending to infinity f of t can be written as limit s tending to 0 s times capital F of s. Okay, so the expression becomes very simple there. Okay, so we take capital F of s and multiply it by s, and then like we take the limit as s comes to 0 for the product. Okay, so that is the final value. Similarly, what is this initial value theorem? Let's look at the initial value theorem. And let's see what we get out of that. So the initial value theorem is the following. So now let's say I want to find the initial condition, okay, of a signal. Okay, let's say I want to find out what the value was when t tends to 0, right, at the start of the process. So then I essentially take limit s tending to infinity s of f. Okay, so in a certain sense, they are complementary to each. Okay, so that's what is called as the initial value theorem, right? As the name indicates, we want to find the initial value of a function or a signal. Okay, that's when this is used. Okay, so going forward, the next property that we will look at is what is called as a complex differentiation theorem. So what is this complex differentiation theorem? So the complex differentiation theorem is the following. If I want to take the Laplace of t multiplying f of t, okay, the function f of t multiplied by t, I want to take the Laplace transform there. So that is going to be equal to minus df of s ds. Okay, so that's what this complex differentiation is. Okay, then going forward, like if you look at what is called as the real integration theorem. Okay, so I hope it's clear why it's called complex differentiation, right? Because we can observe that in this above property, we are taking the derivative with respect to s, right? This is a complex variable, right? So that is why it's called as a complex differentiation, right? So I'm taking the derivative with respect to the complex variable. Okay, so that is idea. That's why it's called. So now real integration. So let me write down what this is, and then it will be. So the Laplace of the integral from 0 to t f of zeta d zeta is going to be equal to capital F of s. Okay, so that is the real integration here. So we can see that we are integrating in the real domain, and we are essentially using that, right? So, and then like we are essentially in the complex domain, the corresponding function f of s is going to be divided by s. Okay? In fact, this is the reason why if you use tools like MATLAB, right? So the integrated block will come as 1 by s, right? So because of this, so when we are integrating a function, like we essentially run it through 1 by s. So you can see that 1 by s is appearing in this formula, right? Similarly, you will see that when we are doing derivative in software like MATLAB, we will use a block which says yes. Okay, so because why this yes comes into play. Okay, so when we take the derivative in the time domain, we are essentially getting this, we are multiplying the signal by S in the complex domain. So similarly, when we are integrating in the time domain, we are dividing by dividing the corresponding complex valued function by S. Okay, so that is the meaning of the, right? So I hope it's clear why we use those notations in this software. So now another property is multiplication and exponential function. Okay, so what is this property? So this useful as we go along. So I will just write down what this property is. So suppose, let us say we have a signal, and then like we have a function f of t. We multiply it by an exponential function e power minus at. So we essentially take the Laplace of e power minus at f of t. Okay. So if we take the Laplace of e at f of t, the result is capital F of S plus A. So what this means is that like wherever we had S, right, we put S plus A, and then like we will be getting the answer. Okay, so that is the meaning of this problem, okay, or meaning of this. Okay, so let me illustrate by using a simple example. Let us say if let's say consider let f of t be some cos omega t. Okay, so as we just wrote down in the table, f of s, which is the Laplace of f of t, which in turn will be the Laplace of cos omega, going to be s divided by s squared plus omega squared. Okay, so this one. So then the Laplace of e power minus at cos omega t. If we want to do that, so as we know, wherever there is S, we need to substitute S plus A. So we will have S plus A divided by S plus A the whole square plus omega square. Okay, so that's what we do. So you can see that this is how we essentially interpret. Okay, this property. It's a very useful property. Okay, so that's why I thought I should share it with you. All right. So these are the let's say some few properties, like of Laplace transform. Now, having quickly revised Laplace transforms, right? So the question now arises: how does one solve an ordinary differential equation using the Laplace? See, there should be some purpose behind learning this theory as far as our course is concerned, right? So what is the link to our course? Like typically what happens is that like when we do linear time invariant analysis of vehicle dynamics, right? We will get ordinary differential equations with constant coefficients. And then like we want to analyze the system response, we can use the Laplace transform to do the analysis. Okay? So that's a connection to vehicle dynamics. Okay, that is the reason why I am doing all this mathematics. Okay, so we will realize its application as we go further, right, in a few weeks' time. So now the question that arises is that like how does one solve an ordinary differential equation using the Laplace transform? Okay. Before I answer the question, are there any questions based on what we have learned till now? So we have just looked at the definition of Laplace transform and a few properties, right? So that's what we have done. So now we are going to see how we are applying it. Yes, please.
So the complex differentiation theorem, can you just tell me why it is complex? I didn't get it actually.
Why it is called complex differentiation theorem is because of this. You're taking derivative in the complex domain, right?
Okay.
See, yeah, okay. The differentiation of operation is done with respect to S, right?
Yeah. Okay. Good.
Yeah. And similarly, it's called real integration because the integration is done with respect to a real variable, right? So that's why this theorem is called real integration.
Yeah, okay, sir. Thank you.
Yeah. All right. Okay, so let's go on. So as I mentioned, what is the connection? We are essentially dealing with We are going to deal with dynamic models where uh, we typically, as a first cut approximate a vehicle response as LPI. And then, like for such classes of systems, we will get linear ordinary differentials equations with constant coefficients, which could then be analyzed using the Laplace transform. Okay, so that is okay. So the question now becomes, like how does one use the Laplace transform for this? Okay, so let's learn by using doing a few examples. Okay, I'm going to do a few simple examples and then I illustrate. So let us say we consider a first order ordinary differential equation y dot t plus 2yp is equal to u of t. As we know, for us, we have a system, u is the input, y is output, right? So let's say the mathematical model of the system is this y dot t plus 2y of t equals u of t. Consequent, and we are given that the initial condition y of 0 is right. We are asked to find the unit step. Okay, so that is the problem at hand. Okay, so what do I mean by unit step response? If we say unit step response, we have to find what is the output when u of t is 1, right? So that is the meaning, right, of finding the unit step response. Okay, so let's see how we can utilize the Laplace transform to solve this problem. Okay, so now what we do is that, like, let's take the Laplace transform on both sides. Okay, we consider that order differential equation, and we are going to take the Laplace transform of that ordinary differential equation on. So please stop me at any point if any part of this example is unclear. I will just do each and every step. So since the Laplace transform is a linear operator, so this will become Laplace of y dot t plus 2 times Laplace of y of t plus Laplace of u of t. Okay, so that's what we will have. Now this is s times y of s minus y0. Okay, the first part. How did I get this? Because from the property that we just wrote down, right? So the Laplace transform, the first derivative is going to be s times the function in the complex domain minus the initial state, right? Initial condition, y0. So that's what we have. Then we have plus 2 times capital Y of s, which is the Laplace of y of t. And let's say for the time being, the Laplace of u of t being u of s. Okay. So right now I'm just proceeding with this. What I am doing is that, like, I'm collecting the terms with capital Y of s. And then I am just going to take the initial condition to the other side. So this will become u of s plus, u of s plus y0. So I hope it is clear what I'm doing, right? So I'm just simplifying, right? So I'm collecting the term containing capital Y of s, which will be plus 2 times Y of s. And that's going to be equal to u of s plus y0, small y. So once we have this, our capital Y of s will become now 1 divided by s plus 2 times u of s plus 1 divided by s plus 2 times y of 0. Okay, so that's what we do. So I just divided both sides by 1 by s plus 2. Now there is some interesting physical interpretation for this. Okay, so the first part of the response function, okay, what is called the response function. Y of s is the Laplace of it, right, in the complex. So the first part on the right hand side is the response of the system due to the input which is given. Right, so I'm sure all of us can recognize that, right? Because we have 1 by s plus 2 times u of s, right? So obviously it is depending on the input u. And this is what is called as a forced response. Okay. Part of the system response, right? On the right hand side, we can see that this contains the initial condition, y0. So this is what is called as the response due to the initial condition. Okay, so this is what is called as a free response. So in general, the response of a dynamic system consists of these two components, the forced response and the free response. So the free response is due to non-zero initial conditions. The forced response to the input which is provided. Okay, so that's something which we need to remember. Now, in this problem, we are given that the initial condition is 0. Right? We are given that y of 0 is 0 and u of t is 1. Right? That's because we need to find the unit step input. Right? Sorry, unit step response. Right? So u of t is 1. So if u of t is 1, this immediately implies that u of s is going to be 1 by s. Right? Why? Because the Laplace transform of 1 is going to be 1 by s. Right? So we have got u of s. Now we just substitute. So what will be our output function or the response function? It will be y of s, and we will get 1 divided by s times s plus 2, right? Because the second term on the right hand side will vanish, right? Because we have y0. Now we can see that we have got the response function or the output function in the complex domain. Okay, so this is good. But then, like, you and I want of t, right? So ultimately we want to interpret in the time domain. So the question now becomes as to what do I do, right, to get y of t? How does one obtain y of t from y of s? Okay, so it's an important question, right? Isn't it? Right? Because we have to get now function y of t from this y of s, right? So which we have done. So the answer to that is essentially we need to take the inverse Laplace transform. Okay, so we do what is called as inverse Laplace transform operation. I'm just going to teach a very simple technique that we will do, right? And this technique is what is called partial fraction expansion. I will do it a few times, and I'm sure as we go along in this particular, I'm sure you will become what to say very good at doing this, right? If you have not already learned it. Okay, so but I'm sure all of us would have learned it at some point. Okay, so in a certain sense, this is only a recap. So, so what is our y of s? It is essentially 1 divided by s times s. So in partial fraction expansion, what we do is that like we essentially split it into different terms. Okay, so this becomes, I can write it as 1 by s and then like 1 divided by s plus 2, right? Is it not? I can rewrite this expression into these two terms. Okay, what I'm going to do is that like we want to find numbers a and b such that I can rewrite this product of 1 by s and 1 by s plus 2 as sum of a by s plus b by s plus 2. Okay, so that's what we want to do. So that is why partial fraction expansion. Okay, so we are essentially looking at the overall polynomial, overall function, and then like we are essentially dividing them, right, into multiple factors, right? So that's what we are doing. So essentially, these are what are called residues. Okay, so these parameters a and b are called residues. Okay, and the question is, how do we find these residues? Okay, so there are simple methods to find them. I'm going to teach you one method. So let's say I want to find the residue a. So what we do is it like we multiply both sides by the factor s. Okay, and the factor s appears in 1 by s, right, on this side, right? So you can see that the factor s appears here. So I just want to find a. So you multiply by the polynomial which is in the denominator of a, right? And the denominator of a contains s, right? And that is what we multiply. and the root of this polynomial s. Okay, so what do I mean by root? The value of s which makes it 0. So in this case, it becomes very simple. The root of s is s equals 0, right? So that's something we need to do, right? So we will see how we will be using it shortly. Now, if I multiply both sides by s, in this side s will cancel out. So on the left hand side, I will just have only 1 by s plus 2. On the right hand side, I will have a plus b times s divided by s plus 2. Okay, so I hope it's clear what I did, right? So when we multiply by s, you can see that on the left hand side, there is already a 1 by s, right? That 1 by s and s cancel out, right? So that's why we are just left with 1 by s plus 2. Okay, so we do this. Now, of course, on the right hand side, now we have this s coming in the numerator, right? With this b by s plus 2. So now what we do is that, like in this equation, we substitute the root of that polynomial which you multiply, okay, which is s equals 0. So once I do this, what happens? On the right hand side, I get 1 by 2. Sorry, left hand side, I get 1 by 2. Right hand side, I just get a, right? Because why? When I substitute s equals 0 here, right, into this factor, we have a s term here, right? That makes the second term 0, right? So we can see that we have got a very simple method for finding the residue a. So in order to find the residue a, we just multiply both sides by the polynomial which is in the denominator of a, right, associated with a, and then like we essentially substitute the root of the polynomial. Okay, we follow the same process for the other residues. So suppose if I want to find b, what happens? I multiply by s plus 2. Okay, once I multiply by s plus 2, what do you think will happen? You'll get 1 divided by s. Okay, so that's what we have. And this will become a multiplied by s plus 2 divided by s. Okay, so that's what we will have on as a first term on the right hand side. Because now s plus 2 will get cancelled, right? On the left hand side, we can see that there is an s plus 2 term here, right? That gets cancelled on the left hand side. So we will get a multiplied by s plus 2 by s plus b. Okay, so that's what we will. Now, why did I get only b? Because you can see that I already have a s plus 2 term here, right? So that's why that cancels it. Now, what do we do? You know, like we substitute the root of s plus 2, right? The root of s plus 2 is going to be s equals minus 2. So when I substitute s equals minus 2, see, how did I find the root of s plus 2? So if I have to find the root of s plus 2, see, root of any polynomial is obtained by substituting the polynomial equals 0, right? In this case, the polynomial is s plus 2. So if I substitute s plus 2 equals 0, I get s equals minus 2. So obviously, when I substitute s equals minus 2, I get minus 1 by 2, and that is going to be equal to b, right? How did I get this? Because we can see that on the first term, a will have a factor s plus 2, right? And when I substitute s equals minus 2, that number goes to 0, right? So that's why we have b to minus 1 by 2, right? So the first term on the right hand side becomes 0 when I substituted s equals minus 1 by 2. So we can immediately figure out that, you know, like we have calculated the two residues. Okay, so this implies that the output function y of s, which is a by s plus b by s plus 2, becomes 1 by 2s minus 1 divided by 2 times s plus 2. Okay, so now what we do is that, like, we take the inverse Laplace transform of it. Once we get it, what we do is that, like, we just go to the table of Laplace transform and write it down, right? So what do I do? You know, like this part, I can write it as 1 by 2 multiplied by 1 by s. Okay, I'm doing all these detailed calculations once so that we are clear about it. And the Laplace transform of 1 is 1 by s, right? So the Laplace transform of 1 by 2s will be just 1 by 2, right? That's it. Okay, so it becomes very simple. Then minus 1 by 2 e power minus 2t. Okay, how did I get this part? Because the Laplace of e power minus at is 1 by s plus a, right? That's something we know. So the Laplace of e power minus 2t, I just substitute s equals 2. So sorry, a equals 2, I'll get 1 divided by s plus 2, right? So that is how we get this expression, right? So for the inverse Laplace transform of y by x, sorry, y of x. Okay, so this is our solution, output function, okay, for the problem under step. So what we have done is that, like, we have solved the what to say ODE. You can double check. Okay, so you can substitute this in the ODE and ensure that we get the ODE is satisfied. You can also double check the initial condition. If you substitute t equals 0, you will see that you will get the initial state as 0. Okay, so please, you can do all those things as exercises. Okay, just to convince yourself that we are on the right path. Okay, yeah. So I hope this example is clear, right? So any before we move to the next example. So are you familiar with this method already? You know, if yes, I can go a bit fast. Have you learned this method before? No.
Yes, a portion of Laplace was in our previous course. It was not extensive. Yeah, a little bit was there.
Which course was that?
It was a part of mechatronics.
Okay, okay. So and but then, like, where you taught how to take the Laplace, inverse Laplace, and so on. That's
Yes, it was there.
so all these things are partial fraction expansion. You're already familiar with.
We were given the charts, sir. So, we learnt it by ourselves, basically, like, few of the things.
Okay.
Yeah.
So
We just use the
anyways,
charts to solve some very basic problems, actually.
okay.
We did
So
it in
anyway, let
autonomous
me go
vehicles
through the
also.
examples. Yeah, I will go through the examples because I also want to ensure that we learn the physics and the mathematics, right? The connection between the two. Okay, yeah, that is my own motivation. All right. So yeah. So do you want me to continue doing examples like this in the class transform domain? Do you prefer that, or would you want me to skip and go faster?
Sir, we can continue, sir. It will be like a revision for us as well.
Yes, it will help
All
us.
okay. So anyway, as we go forward, like you will see that I will speed up the solutions, right? Because the first problem I will solve it slowly so that we understand all the steps. But as we move forward, we will go faster, right? So we will anyway. I will go through another example, right? So now let us say I consider the same example now with a difference, okay? That I am considering the initial condition to be 1. Okay, so initial, in the previous, you can see that it's the same example, not the same example, but the data is the same. But then, like, the only difference is that, like, the initial condition is now 1, right? So the ODE is the same, the input is the same, but the initial condition is no longer 0, it is 1. Okay. So now let us solve this equation. So I will start from the place where we calculated y of s, right? So we already derived y of s for this. So if you recall, if you go back a few steps, we already derived y of s, right? So you can see that this is what y of s was, right? So we already did it. So I'm just going to rewrite that. So y of s will be 1 divided by s plus 2 u of s, 1 divided by s plus 2 y of 0, right? So this is what it is. So now u of s is anyway 1 by s, so this will become 1 divided by, this will still be 1 divided by s times s plus 2, and y of 0 is no longer 0, right? So this is 1, this will be 1 divided by s plus 2. Okay, so this is what we have. So now, what will be y of t? Y of t is going to be equal to the Laplace inverse of 1 divided by s times s plus 2, which is the first term on the right hand side, plus the Laplace inverse of 1 divided by, sorry, something is wrong. A minute. Just a second. Yeah. So this is going to be 1 divided by s plus 2. Okay, so that's the second term. So we already obtained the answer for the first part, right? So we just solved the problem. That's going to be 1 by 2 minus 1 by 2 e power minus 2, right? So this is something we just solved, right? And so this first part is what we already solved, right? So this is the forced response, as we already know, right? So this is the response due to the input. Okay, so now you can help me with the second part. What should be the Laplace inverse of 1 by s plus 2?
d power minus 2t.
Very good. So we just wrote it here, right? So we can see here, right? So that's going to be just e power minus r, right? So this is the second one. So let me mark that also. So that is going to be the free response. Why am I calling it as free response? Because that is obtained by from the initial condition, which is no longer 0. Of course, now I simplify this because there are two terms containing e power minus 2t. So if I simplify this, I will get this as 1 by 2 plus 1 by 2 e power minus 2. Okay, so we can see that this is a solution to this problem. Okay, so the output function is a bit different. The response function is a bit different because the initial condition was no longer 0, right? So, and we can immediately see that as t tends to 0, y of t is equal to 1, right? Because if you substitute t equals 0 in e power minus 2t, you get e power minus 0. E power 0 is 1. So 1 by 2 plus 1 by 2 is 1. Okay, so that's one. And as t tends to infinity, what do you think will happen to the value of y? What do you think happens to the value of y of t as t tends to infinity?
By 2.
1 by 2.
1 by 2. How did you get that? No.
E power minus infinity is 0.
Very good. So if you, when you substitute t tending to infinity, we can immediately observe that e power minus 2 times infinity, e power minus infinity, that goes to 0, right? So obviously the answer will be 1 by 2. Okay, so but you can observe that due to the presence of a non-zero initial state, the response function, right, and the corresponding output of the system, right, whose governing equation was the same, is different, right? So I think that's something which all of us can. Okay, so this with this I have demonstrated how through a couple of simple examples how one could utilize Laplace transforms to solve ordinary differential equations. So once again, why are we interested in linear ordinary differential equations with constant coefficients? If we approximate systems as LTI, the governing equations will be in the form. Okay, and we are going to do that in vehicle dynamics, right, as a first cut approximation. So that's why Laplace transform is pretty useful. Okay, so for our analysis. So that is going to bring me to your first homework. So please do this as homework and submit. Very simple problem. So let's say you consider the system whose governing equation is given by y double dot t plus 3y dot t plus 2y of t is equal to u of t. So this is a second order linear ordinary differential equation, right, in time. Okay, so please take the Laplace transform, find the free response component, forced response component. And then like what I am asking you to do is that like let first you consider both initial conditions to be 0. Of course, this is a second order ODE. So you need two initial conditions, right? So we'll have y of 0 and y dot 0. Both you take it to be 0, right? You take them to be 0 and then like find the unit step response. That is the first problem I want you to solve. And the second one is that like now let u of t be equal to 0. Let y of 0 be equal to 1. Y dot of 0 be equal to minus 1. Find the free response. So now there is no input, but then like you need to go back to the Laplace transform of y of t, and then like substitute y of 0 equals 1, y dot of 0 equals minus 1, and take the inverse Laplace transform of the corresponding function to get y of t, and that will be your free response. Okay, so please do this homework. I will give you instructions on how to submit it shortly, but please do this. Okay, so this is your homework number 1, which you need to submit. Okay. So any questions on this? So if there are no questions, let me stop today's class here. I will stop recording. Thank you for your attention.